Hi, welcome to Slant Asymptotes for Advanced Pre-Cal. The video Ms. Tackett had showed you a certain situation where there was not a horizontal asymptote. And in fact, in that situation, the asymptote is a slant asymptote, and we're going to explore how that comes about today in this lesson. So for these three examples, we'll look at how a slant asymptote can come about. We're going to graph this function in Desmos or your graphing calculator, and then we're going to put it on this graph right next to these directions. So we ought to see a slant asymptote when we do graph it. And what I'm also going to do is factor it, because we're going to use that information to determine characteristics of these rational functions. So we've got x times x minus 1 over x plus 1. Cool. And that's also telling us a few key parts like the x and y intercepts. And we'll mark those down here in a second. Now, when you're graphing these, if you were graphing them by hand, the vertical asymptotes should go in, and we should be able to notice the slant asymptote here as well. But for now, we have some clear points that we can sketch onto this graph. Now, it already looks like there is not a horizontal asymptote on this graph, but we're going to be double sure of that after we figure out the slant asymptote. Now, the vertical asymptote we've already figured out is at x equals -1 because of the denominator, equaling 0 when x is equal to -1, and it doesn't divide out, so it's not a hole. So there are no holes. The x-intercepts are when the numerator is 0. So I've got 0, 0, and 1, 0. Then our domain is -infinity to -1, -1 to infinity. So bread and butter stuff with functions. Now, our slant asymptote will appear, or we'll be able to see it after we divide, so after division. And the best way to divide this function that we've got is to use our synthetic division. If you want to do long division on this function, you can, but synthetic division is easiest. So I'm going to use my -1 that I know is the 0 of my denominator. Remember, if your factor that you're dividing by is x plus 1, then what you want to divide by in synthetic division is -1, the number that makes that 0. So now I can write my coefficients of x squared minus x, so that's 1 minus 1. And x squared minus x is the numerator, but what we might have missed from dividing is if we're given x squared minus x, then we know that there's a third term missing because there is an x to the 0 term, the constant term that's missing. So the coefficient on the x to the 0 term is 0. So we have to write 0 for our division with synthetic division. The division works out like so: 1, -1, -2, 2, and 2. So the resulting division, the quotient, the resulting answer to the division problem is x minus 2 plus 2 divided by x plus 1. Now, what we've actually found is this x minus 2 without the remainder is the slant asymptote. So you can mark that as your slant asymptote. And then the remainder, if you remember what Ms. Tackett said about division, or comparing the numerator's degree to the denominator's degree, this asymptote, this little almost mini problem has a horizontal asymptote of y equals 0. So the horizontal asymptote does not affect the slant asymptote as much as the slant asymptote affects the horizontal asymptote. So that's why we basically ignore the quotient when we divide, and we just use the slant asymptote as the answer to the division problem without the remainder. So if we sketch this on our graph, I'll go to -2 and pass through that with a slope of 1, and I'm getting this slope, or this line. There we go. So we just graphed the slant asymptote on this function. And this box here, this is the biggest point about the entire worksheet, is we know slant asymptotes in rational functions when, and you can remember this term from Ms. Tackett's video and notes, when nx's degree, the numerator's polynomial, is greater than the denominator's polynomial degree, dx's degree. Sorry, I wrote a little large there. Now, what I'm going to do in 2 is figure out all these characteristics and then divide and see if you got the same answer as me, and then we'll rejoin for number 3. Here's my number 2, and I filled in the characteristics. The graph is just a sketch, and it's just so we can observe these features. So don't get stressed out about getting these points exactly correct, but you should know from the vertical asymptotes and the slant asymptote where this graph is generally going to fit, even without graphing it. So I divided x cubed by x squared minus 1 to figure out the slant asymptote, because, again, I see that the degree of my numerator is greater than the degree of my denominator. So I can't do any fancy horizontal asymptote tricks where I just look at coefficients or anything. I have to divide. And not only that, but when I divide x cubed by x squared minus 1, I have to add in 3 placeholders for x cubed, because I've got a second degree not represented, a first degree, and a 0th degree not represented. So keeping those placeholders would look like this in the division statement. And then the result is x plus x over x squared minus 1. Remember, this has a horizontal asymptote of y equals 0, because the degree up here is 1, the degree in here is 2. So it's negligible to the slant asymptote, and the slant asymptote is actually something really easy. It's y equals x. So that's why I have this orange graph in the middle here, or this orange slant asymptote there in the middle. With this third function, I'm going to figure out all the characteristics and graph what I can. Use a graphing calculator if I don't have enough information, and then determine what the slant asymptote is by dividing. There we have it. We have 3, and I did have to add in a placeholder term at the very back of this division, while making sure to keep those placeholders present throughout the whole division sequence when they were required. And that's just a result because we're missing a linear term when we divide, so we get a 0 term that needs to be present. And our slant asymptote is present right there. The graph looks like this, and just a quick little address about horizontal asymptotes and slant asymptotes, if that hasn't been discussed already. The slant and horizontal asymptotes don't necessarily affect these internal pieces of the graph the same way they do these external pieces. So you won't get a break in the graph necessarily if it's an internal piece like that. And that's just a common pattern that you'll see with these functions. The end behavior is also another important thing with rational functions that we'll discuss in future lessons. If not here, then with limits. So thanks for watching, and I'll see you later. Bye.